On the morning of October 19, 1948, a Swiss electrical engineer named Georges de Mestral returned from a hunting trip in the Alps and sat down at his kitchen table in Geneva. He had spent the better part of 2 hours picking burrs off his wool trousers and out of his dog's fur. The burrs were the seed cases of the common burdock plant, Arctium minus, a weed so unremarkable that most people in Europe walked past it every day of their lives without a second thought. De Mestral, who was trained at the École Polytechnique Fédérale de Lausanne, and whose instinct was to ask why rather than to simply move on, took one of the burrs and placed it under a microscope.
What he saw were hundreds of tiny hooks, stiff, curved, perfectly engineered by 400 million years of evolution to catch on anything fibrous and not let go. He looked at his trousers under the same lens. The wool was a forest of tiny loops. The hooks found the loops. The loops held the hooks. The mechanism was as simple as a zipper and as strong as the connection required. De Mestral spent the next 8 years turning that observation into a manufacturable product. He called it Velcro, from the French velours, meaning velvet, and crochet, meaning hook. By 1955, he had a patent. By 1958, he had a product. By 1959, the product was in the hands of people the Swiss engineer had never expected to meet. It was in the hands of NASA engineers in Huntsville, Alabama. It was in the hands of procurement officers at the United States Army Natick Laboratories in Massachusetts. It was inside classified project folders at the Defense Advanced Research Projects Agency. And somewhere between the Alps of Switzerland and the classified corridors of American defense contracting, a fastener invented by a man pulling burrs off his trousers became one of the most carefully guarded material technologies of the Cold War. This is the story of why a simple hook and loop mechanism built from nylon and polyester became a military secret. And to understand why it mattered so much, you have to understand what had come before it. The problem that zippers could not solve. In 1943, a United States Army Air Force's survival instructor at MacDill Field in Florida wrote a 2-page internal memo that was never declassified, but whose conclusions would echo through American military procurement for the next 3 decades. The memo described what happened when a pilot ejected over cold water in winter gear and had to shed his flight suit quickly. The zipper, which had been standard on military flight gear since 1917, required fine motor coordination. In the North Atlantic in January, with hands that had lost sensation after 2 minutes in the water, fine motor coordination was a resource a pilot did not have. The memo counted 17 cases in a single training year where pilots or air crews had been unable to remove survival equipment quickly enough because they could not operate the zippers. Zippers froze, zippers jammed, zippers required a grip that cold water removed from a man's hands in minutes.
The memo was filed and largely forgotten. The war had other priorities, but the problem it identified did not go away. At the end of the Second World War, the United States military had learned more about the relationship between clothing, equipment, and human performance than any army in history had ever known. They had learned it the hard way, in the Hurtgen Forest and on the beaches of Tarawa and in the cockpits of B-17s at 30,000 feet. They had learned that the interface between a man and his equipment was not a secondary concern. In many cases, it was the only concern that mattered. A rifle is useless in hands that cannot pull the trigger. An ejection seat is useless if the pilot cannot get out of his suit. The military after 1945 began quietly and methodically to think about the physics of the human body under stress and what that meant for every clasp, button,
buckle and fastener worn by American servicemen.
It was into this world that George Demestral's patent arrived in 1955. The men who read about it in the trade journals of the textile industry understood immediately that it solved a problem they had been carrying for over a decade. A fastener that required no fine motor coordination. A fastener that opened with a single gross motion of the hand, even a gloved hand, even a frozen hand. A fastener that could be made waterproof, that could be made to withstand temperatures from -40 to over 200 degrees Fahrenheit, that left no metal parts to corrode or jam or freeze. The Army's Natick Laboratories, which had been established in 1954 specifically to develop soldier systems, the science of equipping a human body for combat, contacted Demestral's licensing agent within 18 months of the patent's publication. What happened next was not announced in any press release.
Natick and the classified fastener. The United States Army Natick Laboratories in 1956 occupied a converted textile mill complex on the banks of the Assabet River in central Massachusetts. The facility employed over 800 scientists, engineers, and textile specialists, and its budget was classified at a level that made its actual funding impossible to determine from public records. Its mission, stated in the broadest possible terms, was to ensure that the American soldier could function physically, physiologically, and mechanically in any environment on Earth where American policy might require him to operate. In 1956, that included the Arctic, the tropics, the high altitude over the Soviet Union, and the vacuum of near space, which the Air Force was beginning to take seriously as an operational domain.
The Natick team that evaluated Demestral's Velcro had a specific operational requirement in front of them. The Air Force's new pressure suits, being developed for the U-2 reconnaissance aircraft and for the nascent space program, required fasteners that could be operated by a pilot wearing pressurized gloves. A pressurized glove reduces hand dexterity by roughly 60%. Under those conditions, a zipper requires assistance. A button is essentially impossible. A hook and loop fastener requires only pressure, the same gross motion used to slap a surface. The Natick engineers tested Demestral's prototype material against that requirement and found that it met every specification on the list. They then wrote a report recommending its immediate incorporation into pressure suit design and placed that report in a classified file.
The classification was not arbitrary. The United States in 1957 was engaged in a reconnaissance program over Soviet territory that the Eisenhower administration was prepared to deny at the highest levels of government. The U-2, built by Lockheed's Skunk Works division under Kelly Johnson, was flying missions over Soviet missile test sites and military installations. Every material on that aircraft, every fastener on the pilot's suit, every component of the cockpit was subject to classification because any detail of the aircraft's operational configuration could reveal information about its capabilities. Velcro, in that context, was not just a fastener. It was a component of a classified weapons system. The Velcro Corporation of America, which had licensed Demestral's patent for North American production in 1958, found itself subject to a non-disclosure agreement with the United States government that prevented it from describing in any public communication the military applications of its product. The company could advertise Velcro to the fashion industry, to the sporting goods industry, to the consumer market. It could not say where the bulk of its actual production was going. For the first 4 years of the company's operation, the majority of its output went to a single government contractor whose name was not on the purchase orders.
The man who understood what he was looking at. To understand why the American government moved so quickly and so quietly, you have to understand the particular mind of one man at Natick Laboratories in 1957. His name was Dr. Howard Hasbrouck, and he held a joint appointment between the Aeromedical Laboratory at Wright-Patterson Air Force Base
and the Natick Human Factors Division. Hasbrouck had spent the previous decade studying what happened to the human body at the interface of machine and environment. What happened to pilots who ejected at high speed, to soldiers who operated in extreme cold, to crewmen who had to perform precise tasks in thick gloves and pressurized suits. He had published 31 classified papers between 1949 and 1957 on human performance degradation under physiological stress. He understood, in a way that very few people in the American defense establishment understood, that the weakest point in any weapon system was always the human operator. When Hasbrouck read the Natick evaluation of Demestral's material, he immediately wrote a second evaluation, unprompted, that classified it at a higher level than the original. His reasoning was recorded in the document and later declassified in 1994. He wrote that the hook and loop fastener represented not merely a superior alternative to existing fasteners, but a fundamental change in the design assumptions of any human-worn system. He argued that every military garment and piece of personal equipment designed since 1920 had been constrained by the physical limitations of existing fasteners, buttons, zippers, buckles, snaps, and that those constraints had been built into every specification, every design brief, every ergonomic study. Remove those constraints, he wrote, and you do not merely improve existing equipment. You render entire categories of existing design obsolete. You begin again.
Hasbrouck was right, and the Pentagon knew he was right. The question was not whether Velcro would be used. The question was whether the Soviet Union would be allowed to see it being used before the United States had finished exploring what it made possible. That calculation, the same calculation that had governed radar, that had governed jet propulsion, that governed every material advance of the Cold War, produced the answer it always produced: classification, containment, and the methodical extraction of every military advantage before the technology was allowed into the public domain.
Mercury, Gemini, and the astronaut who made it famous. In April of 1961, Yuri Gagarin orbited the Earth once in Vostok 1, and the American space program entered a state of controlled institutional panic. The National Aeronautics and Space Administration had been established in 1958 with a mandate to beat the Soviet Union in space, and it was, at that moment, losing. The Mercury program was behind schedule. The Atlas rocket that would carry American astronauts into orbit had a troubling habit of exploding. And the 7 Mercury astronauts, former test pilots who had been chosen for their ability to function under conditions that would incapacitate ordinary men, were providing NASA engineers with a relentless and specific list of things inside the Mercury capsule that did not work as they should.
High on that list was stowage. Inside a Mercury capsule, the available volume was approximately 56 cubic feet, which had to contain the astronaut, his life support system, his instrument panel, his communications equipment, his food and water supply for a mission of up to 34 hours, and a collection of loose items, pencils, checklists, cameras, food packets, that in weightlessness became projectiles at the first vibration. The problem of keeping objects in place in a weightless environment had not been adequately solved by any design the engineers had tried. Bungee cords were insufficient. Velcro, which the pressure suit program had been using in classified applications since 1959, was the answer they needed. The decision to incorporate Velcro into the Gemini spacecraft in 1962 was made at a classification level that kept it out of the public technical documentation released by NASA. The agency was acutely conscious that its spacecraft designs were being studied by Soviet engineers. Every visible detail of a NASA capsule was a data point in the Soviet effort to understand American capabilities. The Gemini program manager at the Manned Spacecraft Center in Houston ordered that the Velcro installation specifications be included in the program's controlled technical baseline.
meaning they were distributed only to contractors with the appropriate clearance and were not included in the unclassified documentation released to the press.
This changed, inevitably, with television. When the Gemini 4 mission in June of 1965 broadcast live footage from inside the capsule, viewers watching on black and white sets across America could see astronaut Ed White reach up and pull something from a surface with a distinctive tearing sound. The engineers in the control room at Houston knew immediately what had happened. The classification of Velcro as a military technology had just ended in the most public way imaginable, live on national television in front of an audience of millions. Within 48 hours, the story had been picked up by the wire services. The Velcro Corporation of America's legal team spent the following week in conversations with government lawyers about what could and could not be disclosed. The answer was, disclose the consumer application. Say nothing about the defense applications still in development.
Vietnam and the lesson of the jungle boot. In the summer of 1965, the first large-scale American combat units arrived in South Vietnam, and the Natick Laboratories entered a period of frantic production. The environment of Southeast Asia destroyed American military equipment at a rate that peacetime testing had never anticipated. Leather rotted, metal corroded, cotton absorbed moisture and did not release it. Laces on boots became habitats for fungal infection within 72 hours of continuous wear in the jungle. The standard issue combat boot, which had been designed for the temperate forests of Central Europe, where NATO planners had assumed the next war would be fought, was failing in the Mekong Delta at a rate that was producing casualties from infection and immobilization that never appeared in the official casualty statistics.
Natick's response to Vietnam was one of the most intensive periods of material research in the laboratory's history. They developed the Jungle Boot, a canvas and leather hybrid with drainage holes and a steel plate in the sole to defeat punji snakes. They developed the Tropical Combat Uniform in ripstop cotton. They studied every point of failure in the soldier's equipment envelope and addressed it with a material solution. And at every point where a fastener appeared, boots, gaiters, load-bearing vests, medical kits, ammunition pouches, the engineers at Natick asked the same question. Could Velcro do this better?
In many cases, the answer was yes. In some cases, the answer was no. The acoustic signature of Velcro separating, that distinctive tearing sound audible at up to 30 meters in still air, made it unsuitable for any application where stealth was required. A soldier moving through jungle at night could not open a Velcro-fastened ammunition pouch without producing a sound that carried through the trees. This limitation was documented in a Natick study from 1966, classified until 1988, which established the acoustic specifications that would govern all tactical Velcro applications for the following 3 decades. Velcro was approved for medical applications, for load-bearing systems not used in close contact operations, and for aviation and airborne applications where acoustic signature was not a factor. It was prohibited in a list of specific tactical applications that remained classified longer than almost any other material specification in the American military inventory.
The Vietnamese who captured American equipment and sent it to Soviet analysts in Moscow understood that the Americans were using a fastener they had not seen before. Soviet textile engineers identified its hook and loop mechanism from captured samples within weeks. But knowing what a material is and knowing how to manufacture it to military specification are 2 entirely different problems. The Soviets spent 7 years developing a comparable material that could meet American performance standards. Their version, which entered Soviet military production in 1972, was inferior in both tensile strength and thermal stability.
The gap between the American and Soviet versions of hook and loop fastener technology, measured in pounds per square inch of shear strength at minus 40 degrees Celsius, was the same gap that existed in military material technology. It was not a large gap, but in the equipment worn by the men who would have to fight in it, a small gap was the difference between the fastener holding and the fastener failing.
The patent expires and the world changes. George Demestral's original patent expired in 1978. From that moment, any manufacturer in any country could produce a hook and loop fastener without paying royalties to the Velcro companies, as the original licensing entity had by then renamed itself. Within 5 years, there were over 50 manufacturers globally producing hook and loop material to varying specifications. The price of the material dropped by 60% between 1978 and 1983. It appeared on sneakers, on children's clothing, on hospital gowns, on luggage. It became so ubiquitous in the consumer market that its association with space exploration and military technology was largely forgotten by the generation that grew up with it on their shoes.
But in the military supply chain, the story did not become simpler when the patent expired. It became more complicated. The specifications that the American military had developed over 20 years of classified research were not patents. They were performance standards, documents that defined with enormous precision the exact mechanical, thermal, acoustic, and chemical properties that a hook and loop fastener had to meet to be used on a particular piece of military equipment. Those specifications remained classified. A foreign manufacturer could produce Velcro-like material freely after 1978. They could not produce material that met the classified performance standards used in American military procurement. The gap in manufacturing precision, the same gap that had existed between American and German parts manufacture in the Second World War, the same gap that John Hall had begun to close at Harper's Ferry in 1819, reappeared in a new form.
The Defense Logistics Agency, which managed military supply contracts, continued to source hook and loop fastener material from a small number of American manufacturers who had developed their production processes in close collaboration with Natick Laboratories over the previous 2 decades. Those manufacturers understood the specifications because they had helped write them. They could produce material to tolerances that competitors who had entered the market after 1978 could not match, not because the competitors lacked access to the technology in principle, but because they lacked the accumulated manufacturing knowledge, the institutional memory, the gauge tradition that had been built up over 20 years of classified development. You cannot read a specification and immediately produce the thing it describes. You have to build the machines that produce the thing, and then build the instruments that verify the machines, and then run the production for long enough to understand where the process fails and why.
That accumulated knowledge could not be declassified. It existed not in documents, but in the hands of machinists and the settings of production equipment and the institutional culture of factories that had been doing classified work since 1959. Demestral had seen the hook under the microscope. The military had spent 20 years learning how to manufacture the hook to a specification that no microscope could reveal. What the Burr made possible. When American forces entered Grenada in October of 1983 in Operation Urgent Fury, the footage broadcast on American television showed soldiers whose equipment bristled with Velcro. By that point, the product had been a consumer staple for nearly a decade. Viewers watching at home saw it as a convenience. The same thing on their children's shoes and their gym bags, now appearing on military vests and flight helmets. They did not know that the specific formulation of nylon used in the hook material had been developed at Natick Laboratories under a classified program.
They did not know that the sheer strength specification that kept a medical pouch closed under parachute opening shock had been written by engineers who had spent 2 years testing hook and loop prototypes in the altitude chamber at Wright-Patterson. They did not know that the acoustic study, which determined where on a soldier's equipment Velcro could and could not be placed, had been classified for 17 years before anyone outside the defense community saw it. They saw a fastener. They did not see the 2 decades of institutional knowledge behind it.
George de Mestral died in 1990 in Comugny, Switzerland. He had become a wealthy man from the early licensing royalties, though not as wealthy as the scale of Velcro's eventual adoption would have made him had the patent not expired. He knew that his invention had been used in the space program. He had been told as much, carefully and selectively, by people who were careful and selective by professional habit. He did not know the full extent of the military applications. The classified files that documented them would not begin to be released until years after his death. He knew only what any careful observer could work out, that the mechanism he had seen under the microscope in his Geneva kitchen in 1948 was, at its root, a manufacturing problem. The biology was simple. The hook was simple. The loop was simple. The question was whether you could make 10 million hooks and 10 million loops to the same specification, every hook and every loop, without a single craftsman touching them with a file.
That question had been answered in the armories of Springfield and Harper's Ferry. It had been answered on the assembly lines of Highland Park and the tank plants of Detroit. It was answered again, quietly, in the classified production facilities that made military Velcro to standards that no competitor could immediately replicate. Every time that question was answered, it was answered the same way. Not by a brilliant inventor and not by a superior design, but by the long, slow, unglamorous work of building systems precise enough to produce the same part to the same specification 10 million times in a row. The burr that George de Mestral pulled off his trousers was a masterpiece of biological engineering, 400 million years in the making. Turning it into a military specification took 20 more years, and the work of hundreds of engineers, whose names appear in documents that were classified before most of them were born. The consumer got Velcro on their sneakers. The soldier got something built to a standard the consumer will never see, specified to a tolerance that has never been fully published, and manufactured by a process that exists nowhere except in the institutional memory of factories that have been doing classified work since Eisenhower was in office. De Mestral saw the hook. America learned how to make it. That difference, in the end, is the only difference that has ever mattered.